Hello, everybody. Welcome to tonight's lecture. Tonight's screencast lecture is going to be concerning phase changes. In particular, tonight is melting. Now, melting you probably know something about from previous school years. Our first thing we need to do, though, is real quick, we need to review a very important concept about thermal energy and heat. When you hold an ice cube, your hand feels cold. Why does that happen? Well, you have your hand, which is made of particles, and those particles are in motion. They're going to be mostly vibrating in place as a solid, and you also have particles in the solid piece of water or the ice cube, and they're going to be vibrating. On average, the particles in your hand are going to be at a much higher thermal energy level than the particles in the ice. They're going to be moving faster, so that means that they're going to be a higher temperature. So your hand is at a higher temperature than the ice, and so thermal energy is going to pass from your hand to the ice, and that is going to increase the temperature of the ice and decrease the temperature of your hand. Our first definition is phase changes. Phase changes are when thermal energy is absorbed or released. Matter can actually change from one state to another. And some of the phase changes that we are going to be studying, we are going to be learning about melting, freezing, vaporization, condensation, sublimation, and deposition. You may be familiar with some of these, maybe some not. Tonight we are going to focus on melting, of course. Melting is a change from a solid to a liquid. Here's a question for you. To melt a substance like this ice cream, do you add energy or do you take away energy from the substance? Or in other words, the ice cream. Do you add more energy to the ice cream to get it to melt, or do you take away energy from the ice cream to get it to melt? To melt a substance, you must add energy to a substance. So we are going to increase the amount of energy that is being added to this ice cream. And you can do that in many different ways. Just the warmth of the room. If it's a summer day, you're sitting out in the sun's radiant energy can warm up the ice cream and help it melt. Your hand holding the ice cream, that's going to conduct thermal energy to the ice cream and allow it to melt. And this is a perfect time to talk about energy levels. So if we have a solid substance, let's just call it solid substance A, or in this case, it could be the ice cream. The solid energy level is way down here. If we melt the substance and it becomes a liquid, the liquid of substance A is at a higher energy level than the same solid. In this case, the ice cream, if it was liquid ice cream, is going to be at a higher energy level than the solid ice cream. And we said before that there is a connection between the thermal energy and the temperature of a substance. Quick review, temperature is the average kinetic energy in a substance. And of course, that the higher the thermal energy, the faster the particles are going to be moving around and the farther apart that they're going to spread. So if we have particles, these particles in a solid, they're going to be vibrating. And as the amount of thermal energy increases, they're going to vibrate more and they can get a little bit further apart from one another. They can spread out, which brings us to our next vocab term is melting point. The melting point is the temperature at which a substance changes from a solid to a liquid. So this is a temperature. It's going to be a number. The melting point is going to be a number of some sort. And this is going to be when that solid actually gets enough vibration, enough motion, enough energy to actually break free from the attraction to its neighbors and become a liquid, so it can actually change position. And if we go back to think about our, I'll sit right here. If I go back to think about our ice cube in the hand, did the ice cube go from all solid to all liquid, or was the process gradual? Just look at this picture right now. You can see that there is some particles of water in liquid form, and there are some particles of water in solid form. And we could see that, so that we could see that as a gradual process. Why is this a gradual process? Why doesn't it just happen instantly where the ice becomes a big puddle of water, or this becomes softer or anything like that? Let's think about that. Well, here you have all these particles in here, and portions of the ice cube may have a higher enough thermal energy to move fast enough to break away from one another and to become a liquid. So these particles down here that are actually in contact with the hand, these are probably going to be vibrating a little bit faster than the particles here. The reason why is that they are in direct contact with the hand, so they're going to be getting thermal energy conducted directly to them. The vibrating particles in the hand are going to vibrate and increase the thermal energy or the motion of those particles. And those particles get fast enough that they can actually break away from one another and become a liquid. An important thing to notice is that as the ice cube melts, the ice cube does not soften. The solid portion of the water is still hard. So this solid, the ice cube, is still hard. It's not softer than the ice cube was before. The liquid particles can change shape and move around, change position. They are not in the same rigid, fixed position as they were in the solid. The ice cube does not soften as it melts because it is a crystalline solid. The particles will stay in a repeating pattern and stay in that position. Crystalline solid. Let's take a look at this video. Ice cream melting time lapse. Melting point of water. Now, we should remember that melting point is an actual temperature. So melting point of water is going to be the temperature at which water goes from a solid to a liquid. These numbers I would expect you to remember. So 0 degrees Celsius or 32 degrees Fahrenheit. They are both exactly the same temperature. It's just a different measurement scale. Kind of like if you have 2.54 centimeters is equal to 1 inch. Please note that at 0 degrees, that's the temperature the thermometer is at in this drawing, that there is solid ice and there's also ice in liquid form. You are going to have both liquid water and solid water or ice in the container at 0 degrees Celsius. Water may be a liquid or a solid at 0 degrees Celsius. Even though solid water at 0 degrees Celsius and liquid water at 0 degrees Celsius, they're the same temperature, are they the same energy level? Well, no, they are not. The liquid water is at a higher thermal energy. Liquid water at 0 degrees Celsius at a higher thermal energy level because those particles can move more freely. The particles in the liquid are able to move around and change position, whereas the particles in the solid are still locked into that rigid crystalline structure. They are not able to move freely. And let's go back to our little handy dandy energy level chart. And you can see that the solid of substance A, now we can substitute ice. So the solid ice is going to be at a lower energy level than liquid of the same substance. Do you remember the two types of solids that we've learned about? And if you take a look at the two, you could clearly see some great differences. Amorphous solids, the way they melt differently than the crystalline solids will melt. We've already learned that crystalline solids do not soften when they melt. An amorphous solid will. So if you get a piece of rubber or plastic, as you heat up or warm that rubber or plastic or wax, candle wax, clay, the clay, candle wax will start getting softer even before it becomes a liquid. And you can kind of see some pictures of that right here. Amorphous solids will soften as they are heated. Here's a video clip, wax melting time lapse. Examples of amorphous solids: rubber, plastic, glass. Glass is a good example. Got a cool video clip for you to check out about artisan glass blowing. Back to our energy level chart. Solid of substance A, let's say this is a glass in this case, so solid glass is at a lower energy level than liquid glass. When you melt the glass, it is at a higher energy level because the particles are able to move more freely and change position. Liquid is at a higher energy level than a solid. You definitely need to know that. Here is a block of ice. If you remember, the freezing point or the melting point of a block of ice is 0 degrees Celsius. 0 degrees Celsius piece of ice, as it becomes a liquid, as it melts, the temperature may still be 0 degrees Celsius. However, you still must add energy to a solid to melt it. So even if the temperature doesn't rise, it doesn't increase, you still need to increase the amount of thermal energy that is in the substance. Here's another video clip. Well, folks, hope you learned something. We'll check it out. And our next edition, we will talk about freezing. Come here. What do you say?
Be careful, kids. Bye.
Look. Oh, you want to show your Play-Doh? All right, you got this Play-Doh for Halloween. You can show the kids. Okay. Ta-da!
Cake.
Yummy. Should you eat Play-Doh? Probably not. It says non-toxic, but I don't think it tastes very good.
It doesn't.
All right.
Ate it before.
See ya.